When we think about black holes, we imagine vast cosmic abysses, devouring everything that dares to cross their event horizons. But what if black holes aren't the ultimate endpoints of matter? What if, deep inside them, something extraordinary is happening? Something that defies our current understanding of space, time, and gravity. Enter the Planck Star, a fascinating and hypothetical object that could change our perspective on black holes, quantum mechanics, and even the nature of the universe itself. A Planck Star is a theoretical object proposed by physicists Carlo Rovelli and Francesco Vidotto in the framework of loop quantum gravity, LQG. It is envisioned as the compressed core of a black hole, but instead of collapsing into a singularity, a point of infinite density where all laws of physics break down, the matter inside rebounds due to quantum gravitational effects. Imagine compressing matter to its ultimate limit, down to what is known as the Planck scale, where quantum gravity dominates. At this scale, the usual rules of physics give way to strange and exotic quantum effects, preventing a true singularity from forming. Instead, a Planck star is thought to emerge, acting as a quantum-corrected remnant inside the black hole, potentially leading to an explosive rebound. The idea of Planck stars is revolutionary because it offers a solution to the information paradox of black holes. Traditional physics suggests that when matter falls into a black hole, it is lost forever, violating the principle of information conservation, a fundamental tenet of quantum mechanics. However, if a black hole contains a Planck star at its core, the information trapped inside may not be lost but instead stored and eventually released. Here is some of the physics behind Planck stars. 1. Quantum gravity and loop quantum gravity, LQG. At the heart of the Planck star idea lies loop quantum gravity, LQG, a leading theory attempting to unify general relativity, Einstein's theory of gravity, with quantum mechanics. Unlike traditional physics, which predicts singularities, LQG suggests that spacetime is made of tiny, discrete loops, much like atoms make up matter. When a star collapses into a black hole, classical physics says it keeps collapsing indefinitely, forming a singularity. But LQG suggests that at an incredibly small scale, around the Planck length, 10 cubed to the power of 5 meters, gravity becomes repulsive due to quantum effects. This repulsion halts the collapse and causes the black hole's core to bounce back, forming a dense, extremely compact object, the Planck star. 2. The slow explosion of a black hole. One of the most intriguing aspects of Planck stars is the idea that they could cause black holes to explode, but in an incredibly slow-motion way, at least from our perspective. Due to time dilation, an effect predicted by Einstein's theory of relativity, the rebound of the Planck star inside a black hole might take an enormous amount of time from an outside observer's perspective, possibly longer than the current age of the universe. But from the perspective of the matter inside the black hole, the process might happen relatively quickly. This slow explosion would allow the black hole to eventually release its information and energy, solving Hawking's information paradox, one of the biggest unresolved mysteries in physics. 3. Could we observe a Planck star? Observing a Planck star is incredibly difficult because it resides within a black hole, hidden behind the event horizon. However, if black holes do explode due to the slow release of their trapped energy, we might detect the remnants of such explosions in the form of high-energy gamma-ray bursts or other radiation signals. Astronomers are already scanning the universe for such signals, hoping to find evidence that could support this fascinating hypothesis. What is the relation between Planck stars and the Big Bounce hypothesis? The implications of Planck stars go beyond just black holes. They could also reshape our understanding of the Big Bang itself. Some theories suggest that instead of emerging from a singularity, the universe could have undergone a similar quantum bounce. In other words, our universe might have been born from the collapse of a previous cosmos, rebounding into existence much like how a Planck star rebounds inside a black hole. If true, this would mean that the universe didn't emerge from an absolute nothingness but rather from a pre-existing state, giving rise to a cyclical model of the cosmos. Planck stars offer an exciting and hopeful perspective on the fate of black holes and the nature of our universe. They challenge the idea that black holes are one-way doors to destruction and instead suggest that they could be gateways to future rebirths. Like a cosmic phoenix, matter and information might not be lost forever but instead preserved and eventually released in a slow and magnificent explosion. Though the concept remains theoretical for now, advances in quantum gravity, observational astrophysics, and black hole studies may one day provide evidence that these bizarre but beautiful objects truly exist. If they do, Planck stars will rewrite the laws of physics and deepen our understanding of the universe in ways we can only begin to imagine.